isomerism. Let's discuss today optical isomerism. So this is a part of stereoisomerism. In this we will be talking about optical isomers. Let's first consider what is plane polarized light. See, ordinary light has vibrations in all the planes, but plane polarized light has vibrations only in one plane. As we can see in this is ordinary light and it has vibrations in all the planes, while the plane polarized light has vibration only in one plane. Plane polarized light is obtained by passing ordinary light through nickel prism. So it absorbs the vibrations of other planes, leaving one plane. Optical isomers, they differ in the action on plane polarized light. Optical activity is due to molecular asymmetry. So here we'll be talking about the nature of optical isomers. Basically we have two types of optical isomers. One is the one which rotate the plane polarized light towards right hand side, that is called as dextrorotatory, and another one which rotate the plane polarized light towards left hand side is called levorotatory. So optical isomerism is exhibited by compounds which are achiral. Achiral means they do not have any molecular symmetry. So how we will identify that whether they have molecular symmetry or not? So we look for the elements of symmetry like plane of symmetry and center of symmetry. We will be discussing these two later on. So let's first talk about conditions for compound to exhibit optical activity. The compound should be chiral, that is, it should be asymmetrical, and the mirror image of the compound should be non-superimposable. Non-superimposable means as if we see alphabet A, this is the mirror image, this is the mirror. We can see that this mirror image is superimposable, while this C, if I keep this C on its mirror image, it is non-superimposable. So the molecules which are non-superimposable on the mirror image are called chiral molecules. So if the condition 1 is fulfilled, the condition 2 will be automatically fulfilled, and if the condition 2 is fulfilled, condition 1 is automatically fulfilled. These are basically interdependent. So let's talk about plane of symmetry. Plane of symmetry is the plane. It's a plane, or we can imagine a mirror here. It is a plane passing through the molecule such that molecule is divided into two equal halves, one being the mirror image of other. As we can see, this half part is the mirror image of the other half part, and this plane where we have kept the mirror is called plane of symmetry. So this plane would just behave like a mirror where it can form these mirror image. The one half part of the molecule is mirror image of the other half. So this molecule is optically inactive because it has plane of symmetry. Actually what happens in this is, this half part of the molecule, it causes rotation, but that rotation is cancelled by this another half. The one half part of the molecule, it causes rotation in one direction, while this causes rotation in another direction, and the resultant rotation gets cancelled. So there is no retrotation in plane polarized light. Such compounds are called mesocompounds. This term is very important. Mesocompounds. So the optical rotation caused by one half of the molecule is cancelled by another half. So the character of mesocompound is they have plane of symmetry. Now let's consider the second part, center of symmetry. Center of symmetry, it is a point. Center of symmetry is a point. It's an imaginary point from which if we move equal distance in opposite direction, we will encounter the same atom or groups. Like as if we see from this point, I move in this direction, here we have carboxylic. I move in opposite direction, here also I have carboxylic group. So if I move in this direction, I encounter methyl, and in opposite direction also I encounter methyl. The same is the case with hydrogen, and for these carbon atom also. So this center of symmetry is seen in even carbon containing ring, even number ring. Right. So if any molecule has plane of symmetry or center of symmetry, that molecule will be optically inactive. So a very easy way to identify whether a molecule is optically inactive or optically active is we look for chiral carbon or asymmetric carbon atom. It is that carbon which has 4 different atoms or groups attached to it. As we can see, this is carbon. We have one hydroxyl group, one methyl group, one hydrogen and one carboxylic group attached. All the 4 atoms or groups should be different. Such carbon is called chiral carbon. So if an organic compound has one chiral carbon atom, that compound will be definitely optically active. So as we can see, if I draw the mirror image of this, so as you can see, this OH group, it will come on left hand side, earlier it was on right hand side. So if I take this molecule and I just take it like this and keep on this, so OH will come on this H and this H will come on this OH. So this will make it non-superimposable. So H will have this OH on it, so that will make it non-superimposable. So the mirror images which are non-superimposable, they form enantiomers, the 2 compounds. So these are the stereoisomers which are non-superimposable mirror images of each other. So out of these 2, one is dextrorotatory while the other one is levorotatory. So out of these 2, anyone can be dextro and anyone can be levo. That is absolutely determined experimentally. So out of the 2 enantiomers, one is dextro, other is levo. So next we have racemic mixture. If we have these both molecules present in equal amount, so what will happen? The resultant rotation will again get cancelled, because these 2 isomers which are called as enantiomers, they will cause optical rotation but in equal and opposite direction, due to which the resultant rotation will be 0, and such a mixture is called racemic mixture. So let's discuss this important compound. So this is 2,3-dibromobutane. So in this case, these structures are possible. Both the bromines may lie on same side or on different side, as we can see. So what will happen is, when the 2 bromine atoms are on same side, this molecule will have plane of symmetry. This is meso compound, as we have discussed earlier. So this would be optically inactive. So it would be indifferent from its mirror image, rather 1 and 2. These are mirror images, but they are indifferent. They both are same or identical. And this forms one compound only. These are not 2 different compounds, right? And it is optically inactive. But in spatial arrangement, if the 2 bromine atoms are not on the same side, here the story is little different. So we can see that these will form non-superimposable mirror image, because this bromine will come on this hydrogen and this hydrogen will come on this bromine. So it is non-superimposable mirror image. So what will happen is, it will form an enantiomer, right? So for this we have 3 isomers. 2 are an enantiomeric pair. These 2 are an enantiomeric pair, and 1 we will have this optically inactive meso compound. So total we will have 3 isomers, right? So 1 and 3, you can see there is a difference in the stereochemistry of bromine. These are called as diastereomers. Very important definition. These are the stereoisomers. As we can see, 1 and 3 are stereoisomers because they differ only in spatial arrangement. And these are not mirror images of each other. 1 and 3 are not mirror images of each other. That is why these are called as diastereomers. Right. So another important thing is, some students think that these are non-superimposable mirror image because bromine is not lying on this hydrogen, but actually this is superimposable on itself as it has plane of symmetry. So it will not exhibit optical isomerism. So we cannot say it like these are non-superimposable mirror images, because these 2 are identical only. Right. Thank you.